finish SQL today. We're going to wrap it up by continuing to build this film database that we started on last time, where we have this film table. We decided that it should have certain things. For example, it should have a film ID, a unique identifier. That's our primary key. It's an integer. It's not allowed to be null, and we allow the database to take care of it for us by automatically incrementing and assigning a unique key value to each record that gets inserted. Any attempts, since it's a primary key, any attempts to insert duplicate records are going to end up being rejected by the database. Right? Then we decided, of course, we needed a title, which is going to be a varchar variable character, which is a string. Yeah, go ahead. Some of them, yes. Int, I think you can go with some of the things you can move around, but generally you want the order. Sometimes matters. For example, not null. You can't separate those. You can't go not auto increment null, right? So this is generally how I do it. Integer, it's a primary key, and then the modifiers come after it. Right? Varchar 255 is not allowed to be null. The default, of course, is to allow missing data. The release date, that's much smaller. It's only varchar 50 because we're only going to be using this kind of date format here. It's not allowed to be null, but we provide a default. So if somebody inserts a record without specifying a release date, then this kind of placeholder value is inserted instead. We also decided that we want gross earnings, which is going to be a double. That's going to be an IEEE 754 floating point number, blah, blah, blah. It's just, you've got 17 digits of accuracy, okay? You've got an IMDb rating, which is much smaller, a float, because we only need, say, 4 digits of accuracy there. That movie received 8.35 on average or something. And then we looked at EIDRs, which are external natural keys. A natural key is like a social security number, or an NUID number, or an ISBN for a book. Those are external to our database. We decided that we wanted to model them, and so we've got a varchar 100 here. But we didn't want to use that as our primary key, because if the external authority that's responsible for those keys screws up and issues duplicate keys or multiple keys to the same key to different things, then that would screw up our database. So what we're going to do is we're going to model that by capturing that value and ensuring that it's unique, a unique key in this case, but we're not going to use it for the structure of our own database. We're going to have our own primary keys generated here. That way, if somebody screws up and we need to come in and change an EIDR or an ISBN or an NUID or something like that, then we can come in and change one column value of one record in one table, instead of having that error permeate throughout our entire database and touch dozens upon dozens of different tables. Okay? So let's continue. Right? That's a first good start here. In fact, let me use my database. That's my database there. Of course, you'd need to use your own database. And let me go ahead and create a film. It failed. Why? Let's see. Film table already exists. Right? This is because I was demonstrating this last time in another section, and I already created this table. Right? Well, you're going to have that same problem that if you create a table, okay, now I need to get rid of it because I need to change it. I misspelled IMDb, or I want to go ahead and just with my own rating or something like that. So what you can do is you can get rid of it. Drop table film. And I'll go ahead and execute that. It dropped the table, including wiping away every single record that I ever put into that table. Right? And now you can go ahead and recreate it, and green means good at the bottom there. Right? Green means okay. Well, I don't want to have to go back and forth every single time I'm going to make changes. I want to run this script in its entirety. So one thing that you can do is you can conditionally drop a table. Only drop a table. Let me go ahead and drop the table again and again and again and again. Of course, it's going to be an error because that table no longer exists. You can't delete it twice. So I'm going to put a condition on this. Drop table, but only if it exists. So drop the table if it exists, and you see now down here that it's a warning. It doesn't kill the rest of the script. And I can go ahead and create the table. But if I create it twice, again, that same error as before. So let me go ahead and make that conditional as well too. Create table if exists. If it exists, do you want to create it again? No. If not exists. All right, there we go. And now I can run the entire thing all at once and multiple times without ever having to worry about what tables are there, what tables are not there. Okay? So I'm going to go ahead and create the table if it exists, or drop the table if it exists. Right? But if only if it exists, or not exists, the other. Right? All right. So let's go ahead and continue here. What else do we want to model here? I think I started out by saying, well, let's go ahead and do some films and maybe a director. Right? So should I put in a director in here? Let me go ahead and try that here. A director. Well, what's its type? Give me a director. Your favorite director. Quentin Tarantino. Okay. What is Quentin Tarantino? Is Quentin Tarantino a string? Right. Quentin, comma Tarantino, or Tarantino, comma space Tarantino, Quentin, right? First name, last name, whatever, right? Should I just be modeling this with just a simple string? Probably not, right? I probably want to create another table, just like if you were doing this as objects, right? And you had a film object and a director object, you would probably want two different objects there, and use composition to achieve the relationship between them. That an owner, or that a film would own an instance of a director, and a director might just simply be a person, just like your assignments or your project right now. You've got people, but there are different roles that people can have. They can just be a regular old person. They could be a broker, and then there are two types of brokers. You could be a junior broker or an expert broker, right? So you probably want to make different objects to capture those and model those kind of relationships. We're going to want to do that in a database with another table. So let me go ahead and create table if not exists. Right? I'll just go ahead and go off the bat like that. And what should I call this to model a director? Director. Should I do this? Small d and plural? No. Void pluralization. Make sure that you are consistent about it. That if I used upper camel casing for film, I'd better use upper camel casing for director as well. Now, what is a director? Define a director for me. You said Quentin Tarantino. That tells me that there's a name, varchar 100. Just a name? No, probably want to distinguish between a last name and a first name, varchar 100. Now, by default here, by not saying that they're not null, they're allowed to be null. So you could insert a director called null, right? With no last name, no first name. Maybe you don't want that. Maybe, well, sometimes people don't have first names and they're just known as who directed Terminator? One of the terrible, bad Terminators. What was his name? It's like, there's just a single word, right? Nobody remembers. All right, nobody remembers the movie, obviously, because it's terrible. Not James Cameron, but like one of the terrible ones in between. So last name, first name. The order here generally doesn't matter, but if you want to put first name, last name, that's okay too. That just depends on, that just means that when you select it out without aliasing or rearranging your columns, then that's the order of the columns are served to you when you query something out. Last name, first name. We'll go ahead and say that a last name is not allowed to be null, but a first name, that's optional, right? You could also add middle name, title, suffix, all that kind of stuff. I'm going to keep it simple, though. Is there anything else, though, that you might want in this table? Okay, so a primary key, a way of uniquely identifying each director. Not that there's two Quentin Tarantinos in the world, but who knows, maybe there's Quentin Tarantino Jr. or whatever, right? Director ID. I will use the same exact design up above. Oops. That it's going to be an integer, primary key, not allowed to be null, and it's going to be auto-incremented so that it takes care of it for us. Again, look at the naming convention. I'm using the table name followed by ID, and it's all lower camel casing. Okay? Now let me go ahead and run this entire thing. It didn't work. You have an error in your MySQL syntax. Oops. What did I? All right. There's something else. For the director ID, I don't see create table if not exists director, comma, comma, comma. I'm not seeing anything immediately. Let me go ahead and just try this by itself. Okay, that worked. There's something else. Where is director ID? Okay, fine. Let's go ahead and do the entire thing. All right, and I probably want to drop the table up here as well to recreate it. Director. Save this. Let me go ahead and move this up so I can see it. Clear this out, and let's run the entire script. There we go. All right, the entire script. We drop the table if it exists, drop the table if it exists, create that table, create that table. But right now, is there a relationship between those two tables? No. What should the relationship be? A director directs a film, right? If they're an unsuccessful director, they only direct one film. But a successful director will direct how many films? Multiple, right? So at least we have a one-to-many relationship over here. Directors to films. Now you can argue that a film might have multiple directors, right? Sin City, I think, had 3 or 4 directors. I don't know what the director guild rules are, that they're film actor guild, writers guild, they have rules that at most 5 credits on a film or something like that. I don't know what the rules are, I don't care. Let's just go ahead and keep it simple. One director can direct multiple films, but one film only will ever have one director. Sound familiar? Kind of like publisher, right? One publisher can have many games, but one game just has one publisher. How do we do that kind of relationship? A director can have many films. That sounds to me like it's a parent-children relationship. And if I've got a parent as the director and films as the children, then where do I need a foreign key? The children will need to refer back to its parents. So the foreign key belongs in the film class, right? Director ID, right? Which is an integer. It's not allowed to be null. If it were allowed to be null, then that means that you could have, what's a child with no parent? An orphan, a bunch of orphans down here with no reference back up to their parent record up here. Right? We don't want that. We want to make sure that we have nice, clean data. Everything has a director. So I'm not going to allow it to be null. I'm going to make it an integer here because it has to match this thing over here. And I'm going to use the same exact name because then there's no guesswork. The director ID clearly refers to the director table and the primary key in that director table. Now, how do we make it refer to that thing? Right? The way that we make it refer to that thing is by specifying that it's a foreign key. Right? And we can do that in several different ways. I'm going to do it on a separate line. Foreign key, and the director ID, that's our foreign key. You can have a combination of other foreign keys, foo, bar, whatever. I could make a film ID as well, or whatever, but keep it simple. We're only going to have one foreign key here. Right? And it references the director table, and in the director table, it references the director ID. There. Now let me go ahead and try to create this. So clear this out, save this, and it's going to end up failing. It was okay to use this database. It was okay to drop it, the first one. It was okay to drop the second one, but now it failed on creating the film. I did not have a bad syntax here. Let's read what it says. Foreign key constraint is incorrectly formatted. Right? Foreign key director ID, director. Okay. Up to this point, up to line number 6, if I collapse this, do you see anything about directors other than dropping their tables? So kind of like structures from last semester. If you have a structure that owns another structure, the order of declaration matters. If a film is going to refer to a director, then what order do I have to create them in? I have to create the director first. If I move this up here, now director will be created, and film that refers to a director will be happy about that because it already exists. Let's go ahead and clear this out again and run it all again. Hopefully I don't have a syntax error here. Okay, there we go. Yeah, those are just warnings because of course the tables were already dropped. Right? So the order of your table creation matters. If table A refers to table B, B has to exist before A can relate to it or refer to it. Okay. That is a pretty good start. Let's get some data in there so that we can actually, do some things. So if I've got a film and a director, Quentin Tarantino, what was his last film? Once Upon a Time in Hollywood. Okay, let's go ahead and put that in there. What order do I need to put that data in? The director has to exist first. So insert into director. Let's see. We need a first name and a last name, right? And the order here doesn't matter. But if I'm going to put in values, then of course they have to correspond. And I've got to go with Quentin. Is that how you spell it? I don't know. Who cares? And Tarantino. All right. Why don't I have to specify a primary key value here? Why don't I have to specify the director ID? Because it's automatically incremented and created for me. Let's go ahead and make sure that we've got at least, I don't know, 3 records to play with. Quentin Tarantino, give me somebody else. David Lynch. Give me somebody else. Who? Say again? That's Taikiti, what is his name? Okay. Why did you have to choose something so hard? Director of Jojo Rabbit. Waititi, what is his name? There we go. It's Taika Waititi. There we go. First name, last name. There we go. All right, good. Now let's run the entire thing. And we get 1 row affected, 1 row affected, 1 row affected. Of course, I could go ahead and shorten this up. I don't have to repeat that every single time. I could just have a comma-delimited list of values here so that all 3 of those things can go in with 1 query. You see 3 rows affected now, no duplicates, no warnings, et cetera, et cetera. So a way to reduce some typing, but of course I just did a cut and paste anyway, so maybe that's the way you want to do it. Right? Let's make sure that worked. I mean, we know that it worked because everything's green. Let's select everything from director. And we see that those 3 records are in there with auto-generated primary key values 1, 2, 3. By default, it starts at 1. Right? You can go. That's just how this database was set up. It could start at 50 and then go at random numbers if it really wanted to. Right? There are different ways of automatically incrementing to the next key value. Well, let's make some films. Right? So insert into film. I'm going to have to be careful here because what is actually required? A title is not allowed to be null, so a title is required. A release date is not allowed to be null, but I don't have to provide it because there's a default value. Everything else here looks like it can be null except for the director ID. So let me go ahead and just keep it as simple as possible. Title and director ID. Right. Values. All right, so let's go ahead and take care of Taika Waititi. Taika Waititi, Jojo Rabbit, you said? Jojo Rabbit. I assume that's how you spell it. What about the director ID? Another one was Thor Ragnarok. Help me out with spelling. Oh, well, it doesn't matter. All right. It'll just be on YouTube. YouTube will know that I can't spell. Right. What else? What else did he direct? I think Wilder People. Is it? Let's look at his bio here. Wilder People. Hunt for the Wilder People. Okay, fine. Hunt for the Wilder People. There we go. All right. What about all those director IDs? Well, I could go back up here and say, let's see, they got 3, right? But if I do that and hard code this value to 3, 3, 3, oh, I'm losing a bunch of stuff here. But if I hard code this value, what's the disadvantage here? What if I went up here and changed the order, or I put another director here? Give me another one. Say what? Martin Scorsese, I think. There we go. All right. Now, is Taika Waititi director number 3 anymore? No. So maybe I don't want to hold these values here. I could go ahead and do a nested query. So select director ID from director where last name equals YTT. There we go. And make sure that you are using double quotes there. Right? And then, of course, I can do this over and over and over again if you want to. We're not going to get into cursors, but you do have basic variables that you can set this cursor to a value and then reuse that value later in your script. These just need commas. There we go. Let's go ahead and try it again. There we go. There's all of the, everything was successful. Everything's green. Let's make sure that those work. Select everything from film. And look at those records there. Jojo Rabbit, Thor Ragnarok, with all of those default release dates. And the director ID is now 4 because I inserted Martin Scorsese before. Right? So this is a way of future-proofing your test data, basically. Because when you do design your database, you're going to want to put in some test data in there so that you have something to work with. Right? And it can live in the same exact script if you want. And in fact, I think it should, according to the instructions. But we've got a really nice start on a 2-table database here. Let's just make sure that we've got a variety of stuff. So insert into film, values. Let's see. Let's go with Quentin Tarantino. So I'll go ahead and grab these two right here and just cut and paste. Quentin Tarantino, let's see, Pulp Fiction, and okay, Hateful Eight. 8. There we go. I don't know about 8 or 8. I don't know. 8. There we go. And not Tarantino, or not YTD, but Tarantino. There we go. And when I do that, I've got those in there as well, and you can see that the director is different over here. So a nice start to this database here. What else can we do? Films, directors. What else does a film have? Writers, yeah. Actors. Right. Let's go ahead and make an actor table. To do that, I'm going to kind of steal this because an actor is a first name and a last name, actor and actor ID. But wait a second here. Maybe I could redesign this. Maybe I could, because a director is a person, right? And an actor is a person. What if I just had one person table? Right? That might be a lot simpler because they're exactly the same thing. They're both varchars. It's just that, and some directors can be actors. Waititi acts in his own films all the time. Tarantino is in all of his films as well as something. Right? Usually he gets killed or something. And so, you know, you might say, well, we need to simplify this, and there's going to only be one person table, but the foreign keys, which table they refer to, that is what models the role, right? So if there's a foreign key in the film table that's called director ID that refers to the person table and then person ID, you can do that. And then in a separate table, an actor that refers to a film, or we could have an actor ID here, and that foreign key actor ID refers to person ID. That would be another acceptable design. In fact, it would be a little bit better because then you would reduce the redundancy. Then you wouldn't have, for Quentin Tarantino, that's both an actor and a director, you wouldn't have 2 records and 2 separate tables for the same person. Okay? But we won't do that here. What I want to do is something a little bit different for now. So create table if not exists, actor ID. Let's go ahead and run it. Everything is fine again. It created that actor table right there. Now, what's the relationship here between a film and an actor? An actor acts in a film, and if they're a successful actor, they act in many films, right? But a film, does it only ever have a single actor? Some of them, right? I can't think of any off the top of my head, but John Malkovich. Well, there were several people in that, right? John Cusack was in that. Several other people are in that, including John Malkovich. The one I'm thinking of was Harding. There's a movie with starring Harding that it's entirely he's in the car, and there are other actors on the phone that he's talking to, but the entire movie is just him in the car, and he's driving for an hour and a half. But you get the idea that a film can have multiple actors. An actor can be in multiple films. So to get that kind of a relationship, what do we need to do? A many-to-many relationship. How did we do that with games and platforms? What was in between? There was a table. I'd called a join table. Right? And it had a foreign key reference back to the game table and a foreign key reference back to the platform table. So that's what I'm going to do. Let's go ahead and create another join table. Create table, if not exists. What should I call it? I'm bringing together actors and films. I could call it some verb, right? I could call it acts in, right? Or stars in, right? Or from the perspective of the movie, I could call it has stars, has actors, right? I don't like verbs because these are nouns, right? Don't verbize things if that's a word. Let's make it a noun. And the easiest thing to do, or remember, in computer science, there are only two difficult things: cache invalidation and naming things. So I'm not going to get too creative. I'm just going to call it, I'm bringing together actors and film, so actor film. Keep it simple, right? Or film actor. I don't like that, though. Film actor. Right? How is that different from actor? It's just a film actor. I'm going to put actor film. Right? I'm bringing those two tables together. Don't call it a join table, right? Or join actor film table or something like that. Just keep it simple. Right? The KISS principle. Keep it simple, stupid. All right. Actor ID, or not actor ID, but actor film ID to follow the same naming convention as before. But now what's its, I need two foreign keys in here. I need a foreign key to reference the film, and I need a foreign key to reference the actor so that I can bring them together. Actor ID, integer, or int, not null. Film ID, int, not null. And I need to make those into two foreign keys. So just like up here with this syntax, foreign key, the column name, references the other table's name and then the column in the other table. So without having to retype a lot, actor ID references actor and the actor ID in the actor table. Film ID references the film table and the film ID in that film table. There. Now this is actually not a pure join table. A pure join table would only have these two foreign keys in here. Okay. And it's not a pure join table because we've got our own primary key right here. But we can also add other data, like we did with the video game database. When a game is published on a platform, it's published in a certain year. Right? It could be published in 2019 on Xbox, and then it was delayed a year, so it could be published in 2020 on PS4. Right? So we could put other things in here if we really wanted to. To do maybe other relevant data. It's just that I can't think of any. Won an award, right? Maybe. Won award, right? And you can't have Booleans, by the way. It's not something I covered, but you can do it. Won an award, right? This actor, when they starred in this film, they won an award for it. True or false? And you don't want to say that the actor always won an award for every film that they did. You don't want to say that a film won an award for every actor that was in it. So you put it in the join table if you want something like that. I want to keep it simple, right? Okay, we can run this and see if it works, and it does. Why does it work here, and why didn't it choke? Because I'm putting this this join table at the end. Let me go ahead and make sure that I'm dropping things. Drop table if exists. What else do we do? Actor, and then I called it actor film. Right there. Let me go ahead and clear this out, save it, and run it again. It immediately died. Why? Drop table if exists film. It worked before. Why doesn't it work anymore? I've got a join table now referring to it. Can I, parent, child, can you delete a parent? You can delete children, right? Child records as much as you want. But can you delete the parent without, if children are still referring to it? No, because then you have orphans. You have dangling pointers all over the place. Who's my parent, right? So if I created it in a certain order, director, film, actor, actor, film, what order do I need to delete them in? In reverse order. Right? So I created director. Director came first, so that's going to come last. Right? This came last, so it must come first. And then, of course, you can once you've severed the connection between them, it doesn't matter what order you do them in, right? Except what a film refers to a director, so the director would, yeah, you'd have to do the director last. And when I do this, everything is just fine again. Okay. So creation order matters and deletion order matters, both for records and for tables, and they have to be the reverse of each other. Okay. All right, good. We don't need that much data for the films and actors. Let's see. But we do still have some issues here that I want to make sure that we cover. All right. Making something not null means that it's basically required data. That if they do not produce, or if they don't have a last name for that, then that means that the record will not exist. Is there anything for film here that we might also consider bad data? Look at the, well, you can certainly, gross earnings. You can't have negative gross earnings, right? You can have negative net earnings, right? The film cost you more than you made, but you can't have negative gross earnings. IMDb ratings, what scale are those on? Do you remember? Do you know? 0 to, what's a perfect one? 10, right? So what if I try to insert a record with an IMDb rating of -5 or 1 million? Right? Is that bad data? Probably. So what we can do is we can put in a check constraint. Right? Here we go. I'm going to put in a constraint here. Constraint. These are already constraints that this has to be a float, that this one is not allowed to be null, etc. I'm going to put in my own constraint. I need to name my constraint, so I'll call this non-negative rating constraint. If you don't provide a name, one will be provided for you. So I'm just going to go ahead and provide it here. These backticks are not absolutely necessary as long as you don't have weird characters in there. But I'm going to go ahead and put the backticks in there. That is a backtick. That is not a single quote. It is the one that goes like this, right? And it's on your keyboard under the tilde. All right, that's a backtick. Then check that the Internet Movie Database rating is greater than or equal to 0, and IMDb rating is less than or equal to, less than or equal to 10. There. That's a nice constraint. Let me go ahead and run it, and everything's fine. That was good syntax there. We never, let's see. I'm not going to do it, but I'm going to tell you that go ahead and put check constraints. It's good practice. Unfortunately, on MariaDB and MySQL, actually more accurately on MySQL, check constraints are not enforced. It's a quirk of MySQL. So you can go ahead and put constraints on there. They are supported. It's just that they're not enforced on MySQL. They're enforced on Postgres. They're enforced on Oracle DB. They're enforced on a bunch of things. So you can go ahead and design it with all the constraints that you want. It's just that they will not work on the database instance on CSE. Right? The reason that MariaDB, now what you were using on CSE is called MariaDB. It's a drop-in replacement for MySQL. And the reason that it doesn't support it is because MySQL doesn't support it. So the purpose of MariaDB was a MySQL replacement to detach yourself from the big evil Oracle, the company Oracle, that is. But to keep 100% compatibility. 100% compatibility even means its shortcomings and bugs. There are bugs in MySQL that have not been fixed by Oracle for up to 20 years. Maybe that's exaggeration, maybe more like 15 years, that are fixable and very easily fixable in MariaDB. They've even got patches ready to go for the day that Oracle decides to fix them, but they're not doing it just simply because they need to be 100% compatible to be an alternative. So check constraints are one of the things that falls by the wayside. You can, however, do unique constraints. So remember that we were talking about the EIDR. That's has to be unique. As it is right now, though, I could put in many films with the same EIDR. Let me show you. Let's see. Director ID. We'll go ahead and put it at the front. EIDR 1, 1, and 1. And you see that this actually works. Oops, sorry. Oh, no, sorry. I put in I already did this? Oh, I already did this. We must have done this last time? Yes? No? Okay. All right, fine. I was going to show you that it didn't work, but it does. 1, 2, 3. There we go. It was just slow. And you can see the films now. They have all EIDRs 1, 2, 3, and then of course I didn't specify these over here. But one way that you can enforce uniqueness is by putting on a uniqueness constraint, or in this case, I put on a unique key. Here's another secret about keys, and that's not a secret, but here's another reason that you would want keys. Remember last semester, there were 2 ways of searching a very, very large array. What was one of those ways? So you've got a big array of objects, of transactions or something like that. What's one way of searching through it? You start at the beginning and you go all the way in looking for the thing that you're looking for. What was that called again? Linear search, right? So if you've got 1 billion elements, it's going to take you up to 1 billion comparisons to find what you're looking for. But now there was another type of search that we exploited. What was it? Binary search. If this thing is sorted, you can jump to the middle and say, this is the thing I'm looking for, or if not, it's larger. The thing I'm looking for is larger than it's over here, or it's smaller, so it's over here. I'm effectively cutting it in half. That is an exponential speed up. That's what keys buy you, an exponential speed up in searches throughout your database. If you don't have a key on it, then it has to rely on basically linear search. If you do have a key on it, it can exploit that and keep things ordered, not necessarily in order, like an array is in order, but they use these things called B trees, binary trees, basically, to be able to search efficiently. That's one of the last things that we'll look at in this course, binary search trees. So keys are a very good thing. I was working on a database one time and was pulling up documents, like PDF documents based on some ID, and it was taking forever. And one developer said, well, it's probably because they're all PDFs. They're large files. There's a gig here. Or there's a few megabytes there, a few megabytes there. We're just going to have to live with it. And so I went in and started looking at the database structure. I saw, oh, there's no key on the column that they were searching by. I just did one SQL line to add a key to it. The database resorted everything, and magically all of those document retrievals became instantaneous. Right? In fact, I've even got a comic about it on the website. Where is it? Let's see. Computer Science 2. Is there modules? Basically, this is the link to that I've given you for all the videos for this, and then I think I've got the comic. Yeah, there we go. There's a nice little comic, excuse me, that somebody wrote here, expressing exactly the same thing. So you see how common this issue is. This happened to me years before this comic was published. Like this, the incompetent developer over here. I think we've hit MySQL's limits. It's simply too slow. We've got too much data. I was thinking that we need to switch to NoSQL. We need to go to MongoDB or something like that. We've got a 3-month battle plan, frameworks, refactoring, training workshops, internal tool updates. Wait a minute, let me check something. And then this is me right here several years ago, more like 10 years ago, unfortunately. Just as I thought. So here, it's called an index or a key. Index is another name for a key. It made your queries 20 times faster. So very, very simple design kind of forethought can really, really change your project. Okay. Imagine if this person wasn't there and they invested 3 months into refactoring and rewriting everything, right? Just because of one little line, unique key, right? Happens all the time, by the way. Right? Even one character can throw off an entire project and destroy it. Right? Okay, that's good. I'm going to go ahead and take this over and put it in our notes over here so that you have it. I'll replace all this stuff here. There. And let's talk a little bit about the process that we just went through implicitly. It was called normalization. Oh, let me increase the size here. Is that big enough for everyone? There we go. All right. So there are what are called normal forms. There are basically three basic normal forms. Right? There's one normal form, there's two normal form, there's three normal form. There are additional normal forms. There's like fourth, fifth, some sort of a temporal normal form and a bunch of stuff. That's all for like advanced database stuff that you don't have to worry about. This is 99% of everything that you'll use in real life. Right? If you're writing a paper on database theory or something like that, then yeah, you're going to have to know those forms and come up with your own forms or something like that. Basically, they're good design principles, like the solid principles, but for databases. So first normal form is that each attribute in a table is, has only atomic values. So what is an atomic value? An atomic value, the old school way, like several thousand years ago, meaning of atomic. Atomic means indivisible. Of course, we call them atoms nowadays, and we do know that atoms are divisible. But atomic means that it's indivisible, that you can't take it apart any further, right? That every attribute is only one value, basically. Every column in a database table holds only one value, right? Here's a violation of one normal form. Right? Having a comma delimited list of emails. That's directly relatable to your project, right? If a person can have 0 emails or 1 email or 2 emails or 50 emails, that is a one-to-many relationship. The 0 is an option with the many, right? So what you need to do is you need to create another table. Don't store 0 elements or 1 element and then delimit it by a comma, or 3 elements and delimit it by 2 commas. That takes you all the way back to CSV files, right? That takes you back to flat files. And it defeats the whole purpose of making a relational database to begin with. It's also a violation to simply hard code enough columns. Right? So, I mean, it's strictly speaking, it's a violation, but I've seen people do it with, it's not that bad. It's certainly bad to do something like this, having a comma delimited list. This is a little bit less bad to hard code enough columns. So, for example, email 1, email 2. These are the 3 columns: email 1, email 2, email 3. That would be a bad design because you don't have a one-to-many relation anymore. You have a 1-to-3 relation. Right? And sometimes that first one's not used. Sometimes the second one's not used, etc. Right? So it's not as bad, but it's still kind of bad. Just make another table. Right? Simply make another table for any one-to-many relation. Right? And then you're going to be compliant with first normal form. Second normal form is that it has to be one normal form. Let's see, I'm fighting that. There we go. That'll be a little bit better. And no non-prime attribute is dependent on a proper subset of prime attributes. Right? Don't worry about the meaning here. Let's look at violations of it, and then it'll be very, very easy to understand once we see this. Basically, the principles that I've already given you will automatically give you second normal form. If you always create a primary key auto-incremented primary key, you get 2 normal form for free automatically. So if you just follow that design principle, you're going to be 2 normal form. Unfortunately, a lot of databases I see don't follow that, and they want to have really fine-grained control over everything. Let the database do its job. It's very, very good at it, right? Just let it generate those keys and use those keys. But basically, a violation would be something like this. A purchase record may contain a customer ID. I don't know if I want to backtick these or not. A store ID and a store location. Yeah, I'll just do it like this. So why would that be a violation? So it's a purchase record. How do you say that you identify a purchase record with the customer ID, right? And then you've also got the store ID. Those two things together might mean that that's your prime attribute. That's your primary key. The combination of those two things is your primary key. Because a person purchased this product at this store. So this person, this store, that uniquely identifies a purchase. If the person made a purchase at another store, that's a different purchase. If at the same store you had a different person making a purchase, then that's a different purchase. So maybe the prime attributes here are the combination of customer ID and store ID. What about store location? What is that dependent on? Like an address, a store address. Is it dependent on the customer ID? No, it's only dependent on half the key. It's only dependent on the store ID, not the person ID. So that's a violation of second normal form. Split everything out into its own table. Its own table. We see this all the time, even in your projects with Java, with object-oriented programming. Violations of encapsulation, where you didn't define an address class. Or maybe in your portfolio, to identify the owner, all you have in your portfolio class is the a person code, and that's your owner. Right? No, you need an object because the only information you've got is the person code. What if you want their address because you want to print out that summary report? You need to have a proper object in there. You need the proper encapsulation, and in the context of databases, that means you need to adhere to second normal form. Right? Finally, third normal form. Third normal form is that it's second normal form, and of course by transitivity it's also first normal form, otherwise it wouldn't be second normal form. And no non-prime column is transitively dependent on on the key. And again, to understand this, let's go ahead and look at violations of this normal form. Suppose that we had a price per, so let me go ahead and get this. I'm just going to go ahead and bring this over. So suppose that you had a price per unit and a number of units. Well, then what's the total price? Price per unit times number of units. Right? If you stored all three as columns, it is a violation of three normal form, right? Because the total price is transitively dependent on the other two columns. Don't do that. Don't store computed data. Total price, you can always recompute total price with an SQL query, or you load up the database data into memory and you do a multiplication. Right? That does not need to be stored. It can lead to data anomalies because what happens if you come in and you change the unit price? You now have a 10% discount. That third column is now stale. That third column has the wrong data in it. What if you come in and change the number of units? Instead of 10 Xboxes, I want to purchase 20 Xboxes now. Right? Then that other data is stale. That other data is out of sync with the rest of the data. So just don't store stuff that is dependent on other data. Right? Bottom line is that three normal form is common sense intuition. Right? It's you just have to get used to it. We're doing the film and actor database, we kind of did it naturally. We said, okay, well, what is a film? What is a director? Are they the same thing? Violating second normal form? No. We split them out into their other tables. What about an actor? What about a film? What are the relationships between there? Right? It was kind of common sense, or it was kind of natural the way that we designed that database. Hopefully, it came natural. Right? But otherwise, this is summarized with that quote that I gave you before. Every non-key attribute must provide a fact about the key. That's one normal form. The whole key. That's two normal form. And nothing but the key. That's third normal form. Right? So help you COD. Right? So help you COD being Edgar Codd, right? The inventor of the relational database model. Right? Okay. So there's a lot more to learn. This is not a database course, though. There are triggers, views, stored procedures. Security, obviously, don't store passwords. Views are another way of doing security. You can restrict users to read-only access so that they can't screw up your data. You can restrict users to a particular subset of your data. So if you've got 50 tables and you only want to let them see these 3 tables over here, you can grant them view access so that it looks like a completely different database, they only have access to what you grant to them. Don't store passwords, though, of course. At least don't store them unhashed. The vast majority of break-ins, they're going after passwords. And if they see that they're stored plain text, oh boy, that's a heyday. Even if they see that they're stored with a weak hash function, we haven't talked about hashing, but it's in the videos if you want to check it out. That's how passwords are stored. You hash the password so that my password 1234 is not stored as 1234. It's stored as this cryptographic hash that can't be reversed. You also have an issue of hard versus soft deletes. Yeah, that's something that you're going to have to think about for your upcoming phases. A hard delete means that you actually delete a record. In other words, you use a delete query to wipe away the record. An alternative is what's called a soft delete. A soft delete means that you create another column called isActive. Now, to delete something, you set that to false, right? Is it active? No, it's not. And then on your front end, you only query for things that are active. But it's still in the database. Say that you need to undelete it, right? Somebody accidentally deleted it, you need to come back and restore that record. Well, if you use delete, it's gone forever. There is no undelete. But if you design your database to have soft deletes, and this is not something you have to do, it's not even something I suggest that you do for your project, but it is something that you should be aware of. If you can come in and undelete it by simply setting isActive to true, right? So that you can be the hero. In fact, I've designed databases like this. Where I made it so it's soft delete because I know that I've got some ID10T users, and they're going to screw up and delete something that they didn't mean to. And so on the front end, you put in an ominous message that's saying, are you absolutely sure you want to delete this record? This cannot be undone, right? And so they do it anyway. And then they call you up and say, I accidentally deleted those records. I need those back. And you go, okay, well, it'll take me a couple days, but I'll help you here. I've got your back here. All right, and then you go off and you do something, play video games for an hour or two or something, and then you come back and say, you know what? I worked, or no, next day, let's say I worked all night. I worked all night, and so I'm going to report that on my overtime. I worked all night, and I was able to restore those records from a backup from a while ago. All you did was set a Boolean to true. So yeah, you can be the hero. That's how engineers are all the time, right? That's called the Scottie Principle, right? From Star Trek, Scottie would always say, give an overestimate. To get the engines back line, it's going to be 10 hours. And he really meant it was only going to take 2, because then the captain would say, you've only got 5 hours. And okay, well, I'll do it in 2. And now I'm the hero because I worked 5 times as fast as what I told you before, right? It's called estimation. Right? And as long as you're talking to a non-technical person, you can always justify anything you want. But if you're talking to a technical person, then no. They'll probably know that you're feeding them crap. All right. All right, so any questions on databases, database stuff, or whatever? No? There is one other thing that I'll probably save for a post on Piazza because it's a little bit more involved here. But there's an object-oriented programming model versus the relational model. Relational model, right? So one thing that you have to be aware of here is that object-oriented OOP has inheritance and behavior. The relational model, that is databases, do not, right? Strictly speaking, they do not. Data is just data. They don't have a bunch of methods that act on that data, but an object-oriented programming does. Object-oriented programming has inheritance. You don't have that this table is a subclass of this table or a subtable of this table. So you have to come up with some way to resolve this stuff. To resolve the disconnect between the two models, you need some way to model inheritance. You don't need to model the behavior because that's, of course, in your Java classes anyway. So there are three ways. I forget the other two off the top of my head. I'm just going to give you the easiest way. The easiest way to deal with inheritance is like we did in our flat files. You have three different types of assets, right? You have deposit accounts, you have private investments, and stocks. In the CSV file or the data file that you've been processing, how do you differentiate between those three? How do you know that it's a stock asset? How do you know that it's a private investment asset? There's a letter, right? That's called a discriminator column, a discriminator value or column, right? That you denote which type of class a record corresponds to with a single character or other value. It could be like an enumerated type, but we didn't talk about enumerated types, but you could do that as well, right? But the easiest thing to do is with the single character. So that you don't, now there is an alternative. You might think that, okay, I need a table per class. That now it just popped my memory for what the other two approaches are. One of the approaches is a table per class. So if you've got an asset class and a stock class and a private investment class and the deposit class, you'd have 4 tables. And then you'd relate those all together through foreign keys, right? So you could model the inheritance with your tables. That gets really, really complex, really, really fast. Don't do it. I mean, you can do it if you want to, or if you want to challenge yourself. It's just a bunch of extra work, right? This is much simpler. Just to have one table for all assets with one column that has a discriminator value. And the discriminator values in the data files, that's good enough. S, D, and P, right? So that's the easiest way to deal with resolving these two different models, because one of them has features that the other doesn't. Object-oriented programming has inheritance and behavior. Relational databases don't. Right? So that's another thing that you'll want to think about with your design for the upcoming phase. Not the phase due this week, but the phase due in a couple of weeks, where you're designing your database to support this application. Okay. All right, so looking ahead here, next week, it's going to be on Tuesday. Since we've covered everything that I wanted to cover as far as databases go, next week we will have a review on Tuesday. The form that will take is I'm going to bring in the question bank that I randomly generate tests from. There are something like 400 questions. We'll do it on an overhead projector here. They're all multiple choice. It will be done on a Scantron, so you'll need to bring your number 2 pencil, old school style. The reason that we're doing that is because if we do it the modern style, where I have you do it over in the testing center, they don't allow open book, open note, open computer. So I think that that's a pretty good trade-off. Yeah, you're going to have to bring in a pencil. You're going to have to fill out a bunch of bubble sheets, but you can use whatever notes you want. You can use your computer, not to communicate with each other, though. So I think it's worth about 5% of your grade. There'll be maybe 20, 30 multiple choice questions. Again, I haven't made it yet. I auto-generate it with a script. But on Tuesday, we will have that review. On Thursday, then, we will have the entire time will be devoted for your exam. This is all next week. When we come back after that, we'll butt up against spring break by finishing out with JDBC and multi-tier architecture, because after spring break, we kind of change modes and we go into data structures and algorithms mode instead of the practical stuff. Right? Any questions? Tests? Anything? Oh yeah, go ahead. Nothing's cool. I don't know. Coolest? I guess at Werner Enterprises, which is a trucking company up in Omaha, we were on a OpTech team, which is optimization technology. I don't know why they call this optimization technology. We wrote genetic algorithms for load consolidation. So we have like 50 loads, and trucks are going all in completely different directions. Well, you can optimize it by saying just shove everything onto that truck, and have 50 stops along the way. But what we did was we wrote a genetic algorithm to simulate a bunch of things and try a bunch of different things, try a bunch of different routes. And then, of course, the feedback mechanism was how much does that route cost? And so then you saw the minimization of the cost going down. So that's kind of cool. Otherwise, I mean, the most enjoyable thing that I work on is is not something I made, but every year the advent of code. Those are some pretty cool problems. I only did the first few days last Christmas, but I highly suggest those. Those are some cool problems to work on. Similar to that would be Project Euler. That has a bunch of programming problems, but it's all just like toy problems. It's not like solving real stuff. Right? So machine learning, that's kind of cool. Genetic algorithms, kind of cool. I don't know, it's all boring. Anything cool becomes boring after 3 months of doing it. So you always have to be finding something new, right? Okay, next week then.